Everything is made of atoms. But what are atoms made of? Scientists used to believe that atoms were solid particles, like tiny snooker balls. They thought atoms couldn't be split apart. This idea was changed in 1897 by J.J. Thomson. He was investigating the properties of cathode rays using this piece of equipment, an empty glass tube. Here's a modern version of Thomson's apparatus, an evacuated tube containing an anode and a cathode. Heat the cathode and it produces a beam of cathode rays. The beam cuts across a fluorescent screen. Scientists knew that a magnetic field could deflect the path of a cathode ray beam. Turn the magnet round and the beam is deflected in the other direction. Thomson measured the size of this deflection. He worked out that cathode rays were made of tiny particles, hundreds of times smaller than an atom. Thomson was also the first to deflect these beams with an electric field. The screen sits between two horizontal charged plates. An electric field between the plates deflects the path of the beam upwards. The positive plate attracts these cathode rays. The negative plate repels. Reverse the connections so that the polarity swaps over and the beam is deflected in the opposite direction. Again, attracted to the positive and repelled by the negative. From this, Thomson concluded that cathode rays must be made of negatively charged lightweight particles. He'd discovered what we now call electrons and went on to say that electrons were part of all atoms. In 1911, Ernest Rutherford made the next major breakthrough in atomic structure. He was examining the results of an experiment based on this type of setup. A radioactive source emits a narrow beam of radioactive particles. This is directed at a target of thin gold foil. Detectors register the presence of radioactivity at different positions. These displays will show the count rate in each detector. The experiment must be carried out in the dark in a vacuum. Start the detectors at the same time, and the fixed detector behind the gold foil shows a high count rate. Most of the radioactive particles pass straight through the metal film. There's a much lower count rate on the other detector. This shows that a few radioactive particles have bounced back from the gold. But how could this have happened? Rutherford suggested that atoms contained a tiny, dense core called the nucleus, surrounded by lots of empty space. Imagine each snooker ball is the nucleus of one gold atom. And these marbles are the radioactive particles. Aim the marbles at the snooker balls. Most roll straight past to be detected behind our model gold atoms. It's this that made Rutherford think that there must be a lot of space within each gold atom. Our model also shows why some radioactive particles were deflected from the gold foil, having hit the dense central nucleus of a gold atom. Following Thomson and Rutherford, scientists have now discovered lots of particles inside the atom. You need to know about three: the proton, the neutron, and the electron. A proton has a positive charge. A neutron has no charge. An electron has a negative charge. The nucleus of most atoms is made up of protons and neutrons. The only exception is the hydrogen nucleus. It contains just one proton. Each nucleus is tiny compared to the rest of the atom, which is almost all empty space. The only things there are electrons orbiting the nucleus at very high speed. The periodic table is the most popular chemical pin-up in the world. In every science lab, you'll find the elements set out in exactly the same order. The layout isn't alphabetical, but it isn't random either. Every element in the periodic table is arranged in order of increasing atomic number. To understand atomic number, you need to look into the heart of an atom. Take hydrogen, the first element in the table. Orbiting around the outside of each hydrogen atom is one electron. And in the nucleus is one proton. Like all protons, it has a positive charge. Every hydrogen atom is the same. The atomic number is simply the number of protons in the nucleus. A hydrogen atom has one proton, so hydrogen's atomic number is 1. Atomic number is usually written to the bottom left of the element symbol. So what about the next element in the table, helium? What's its atomic number? Helium has 2 electrons orbiting around the outside. In the nucleus, there are 2 protons and 2 neutrons. The atomic number is simply the number of protons. So the atomic number of helium is 2. The next element along the periodic table is lithium. Orbiting round each lithium atom are 3 electrons. In the nucleus, there are 3 protons and 4 neutrons. So what's the atomic number of lithium? The number of protons is 3, which means that the atomic number is also 3. As you move across a row from left to right, the number of protons increases by 1, so the atomic number also increases by 1. An element's atomic number determines its position in the table. Another number you need to understand is called the mass number. The mass number at the top position is usually a bigger number than the atomic number at the bottom. Move along a row, the atomic number increases by a steady unit of 1 each time, but the mass number changes by irregular amounts. To understand mass number, once again, we need to look inside an atom's nucleus. Mass number is the number of protons plus the number of neutrons. Hydrogen has just 1 proton in its nucleus and no neutrons. Its atomic number is 1, and its mass number is also 1. So what about helium? It has 2 protons and 2 neutrons. 2 plus 2 is 4, so the mass number of this helium atom is 4. Next, look inside a lithium nucleus. Can you work out its mass number? 3 protons and 4 neutrons mean the mass number is 7. For every element, atomic number is unique. Each element has a unique atomic number. It's the number of protons in an atom's nucleus. It also tells us the number of electrons orbiting an atom's nucleus. To show how electrons orbit the nucleus, we're using a model. Here, electrons are represented by roller skaters. The orbits occupied by the electrons are circles. The nucleus is the square in the middle. Each atom has the same number of electrons as protons, so if the atomic number is 12, there are 12 protons and 12 electrons. But where are these found? Electrons don't move at random. They circle the nucleus in orbits called shells. Each shell holds a fixed number of electrons. To take a closer look at how these shells are filled, we're going to start with the 3 simplest elements: hydrogen, helium and lithium. Hydrogen has an atomic number of 1. It has 1 proton and so 1 electron. This single electron goes into the first shell nearest to the nucleus. Next, helium. Its atomic number is 2, so it has 2 electrons. They both go into the first shell. But what about lithium, which has 3 electrons? 2 is the maximum number for the first shell, so the third electron has to go into a second shell. There's a limit to how many electrons each shell can hold. The first shell holds a maximum of 2 electrons. The second shell holds a maximum of 8 electrons. The third shell can also take 8 electrons. Using these rules, can you work out the electronic structure of fluorine, which has 9 electrons, neon with 10 electrons, and sodium with 11? First up, fluorine. 2 of its 9 electrons filled the first shell. The remaining 7 go into the second shell. A shorthand way of writing this is to list the number of electrons in each shell. Next, neon. Its 10 electrons are arranged so that there are 2 in the first shell and 8 in the second shell, which can be written like this. But what about sodium? It has 11 electrons. 2 fill the first shell, the maximum of 8 fill the second shell. And so the remaining 1 electron has to go into the third shell. And this can be written . Comparing an element's position with its electronic structure, there are some interesting patterns. Take group 1. Lithium has 3 electrons. Sodium has 11. Potassium has 19. Compare their outer shells. In each case, they hold just 1 electron. What about group 0? Helium has 2 electrons. Neon has 10. Argon has 18. In this group, the outer shell is always completely full. Apart from group 0, elements in the same group have the same number of outer shell electrons. This gives them similar chemical properties. Each row relates to a particular electron shell. Take the row starting with lithium. Look at the electronic structure. The second electron shell is filled as you go across this row. By the end of the row, this shell is full. Then it's time to fill a new shell, and that means starting a new row. So back to the element we started with. If you remember, it had 12 electrons. What's its electronic structure? And what group does it belong to in the periodic table? Proton was also the first to deflect these beams with an electric field. The screen sits between 2 horizontal charged plates. An electric field between the plates deflects the path of the beam upwards. The positive plate attracts these cathode rays. The negative plate repels. Reverse the connections so that the polarity swaps over and the beam is deflected in the opposite. Scientists knew that a magnetic field could deflect the path of a cathode ray beam. turn the magnet round, and the beam is deflected in the other direction. Thomson measured the size of this deflection. He worked out that cathode rays were made of tiny particles, hundreds of times smaller than an atom. Thomson Everything is made of atoms. But what are atoms made of? Scientists used to believe that atoms were solid particles, like tiny snooker balls. They thought atoms couldn't be split apart. This idea was changed in 1897 by J.J. Thomson. He was investigating the properties of cathode rays using this piece of equipment, an empty glass tube. Here's a modern version of Thomson's apparatus, an evacuated tube containing an anode and a cathode. Heat the cathode and it produces a beam of cathode rays. The beam cuts across a fluorescent screen.